Okay, let's start with exercise number 11. Exercise number 11 from oscillations and waves. So exercise number 11. Exercise number 11 from oscillations and waves. Number Exercise number 11. There are oscillations with energy W, in a LC circuit that consists of a parallel plate capacitor and an inductor. What work was done when the plates of the capacitor were moved apart from each other, if the frequency of the oscillations increased eta times? Okay, so let's make a scheme of this circuit to understand what happens in this system. So here we have a simple LC circuit. LC means that it consists of capacitor and inductance. Capacitor and inductance. And here we have induction coil. Induction coil. So we have capacitor, inductance. Capacitor and inductance. Okay, so there were oscillations with energy W, and at a moment in time, some manipulations with capacitor were done, and its capacitance changed, and the energy of oscillations also have changed. So maybe you have some ideas what to do what to do in this case. Maybe you can remember how to calculate energy. So I will give a little hint that during oscillations, energy passes from capacitance to inductance, and again from inductance to capacitance, and so we have oscillations. In which energy passes from capacitance to inductance, and then again from inductance to capacitance. So this energy may be written as energy in capacitor, or energy in inductance, or in general case we have part of energy is concentrated in capacitor, and another part of energy is concentrated in inductance. Okay, so how to define this energy? For example, in case when it is in a capacitor. Cannot remember. Okay. Okay. So I'll remind that it will be QF. QF is a maximum value of charge on capacitor divided by double C, where C is capacitance. Where C is capacitance. Okay, and what will happen? What will happen to this energy? What will happen to this energy after after it leave capacitance and come into inductance? When energy leaves capacitance and comes to inductance, what will be here? How do you think? No ideas. Okay. In this case, all energy, all energy is in inductance, and in this case we have L, electric current, to the power of 2 divided by 2. Okay, and in general case, part of energy is in capacitor, and another part of energy is in inductance. So in general case, we have divided by 2C plus LE to the power of 2 divided by 2 divided by 2. So in this case, we have such situation. We have such situation. So this energy, this initial energy, and after manipulating this capacitor, we will have some another energy, for example, W1. We can sign this as W1, and according to the law of conservation of energy, uh, we can calculate work. We can calculate work as energy after manipulating minus energy before manipulating. So if we find this energy, we will be able to calculate work that is necessary according to the condition of the exercise. Okay, and how do you think? How can we define this energy? Okay, maybe you can remember that uh, we we still haven't used this value. This value. This value is change in frequency. This value is change in frequency. So according to the condition, frequency increased eta times. Increased eta times. So what can we say about this frequency? This value means that frequency after manipulating divided by frequency before, and is equal to eta. Okay, and maybe you can remember formula. Maybe you can remember formula for natural angular frequency. Can you remember how to connect this frequency with parameters of LC circuit? How do you think? No ideas. Okay, I will remind. It will be 1 divided by square root of LC. LC. Okay, and what about omega 1? How do you think? So there was frequency omega 0, and after some manipulation with capacitor, it becomes omega 1. Okay, so what can you say about this situation? What will we have here? It will be something very, very similar to this. No ideas. Okay, no ideas. When we do some manipulating with capacitor, its capacitance changes. So we can say that it will be 1 divided by square root of LC1. LC1. Inductance will not change because we don't do anything with it. So inductance will not change. Inductance will not change in this situation. Okay, so let's substitute these two values here. Let's substitute these two values here. So we will get that eta is equal to is equal to the square root divided by square root of LC, and it will be C1 divided by C divided by C, and so it will be. Sorry, I have made a mistake. We have omega 1 in numerators, in numerator. So we have to write it here. We have to write here. Okay, so we will get capacitance after manipulating. Capacitance after manipulating is equal that is equal to, we have C1 is equal to C divided by eta to the power of 2. Divided by eta to the power of 2. Okay, do you have any questions about this? No questions. No questions. Okay, that's great. That's great. So we have found this, and if we compare this and this, what can we say about energy omega 1? What can we say about this energy? According to the formula that are rounded with blue line. How do you think? No ideas. It's a pity. It's a pity that there's no ideas. Of course, we will get very similar situation. QF to the power of 2 divided by 2C1 and divided by 2C1, and we know that the C1 is equal to C divided by eta to the power of 2. So we will get eta to the power of 2 QF to the power of 2 divided by 2C divided by 2C. And it will be equal, according to this formula, it will be eta to the power of 2 double V. Double V. Okay, do you have any questions? Do you have any questions about this? If there are no questions, we can use this here, and we will get double V minus double V. And it will be eta to the power of 2 minus 1 and multiplied by double V. Okay, this is the answer. This is the answer. Okay, so what questions do you have? What questions do you have about this? No questions. Okay, if there are no questions, so let's do exercise number 12. Exercise number 12. Exercise number 12. A LC circuit consists of a capacitor with capacitance C, and an inductor with inductance L. The coil is in constant magnetic field with flux linkage that we will sign as C, because we have used psi for flux linkage on our lectures. At a moment in time t is equal to 0, t is equal to 0, the magnetic field was turned off. Assuming the time of magnetic field turning off is negligibly small in comparison with natural period of the circuit, find the current in the circuit as a function of time t. Magnetic field was turned off rapidly, and oscillations appeared in this circuit. So, and we have to find dependence between electric current and time. Okay, do you have any ideas how to do this? No ideas. But we can use for example, we can use differential equation of for small oscillations. As you can remember from our last lecture, for forced oscillations, we have differential equation that contains second derivative of charge q plus 2 beta dq dt plus omega 0 to the power of 2 q and it is equal um divided by L cosine omega t. Okay, but in this situation, we don't have any resistance because we have a simple LC circuit. We don't have resistance, so beta damping coefficient that is equal to R divided by 2L is equal to 0 because we don't have any resistance, and we also don't have a generator. We don't have source of electromotive force. We don't have source of electromotive force, so it means that Um is also equal to 0. Um is equal to 0, and so it means that we can rewrite this equation. And we can rewrite this equation as a second derivative plus omega 0 to the power of 2 q, and this is equal to 0. Okay, and maybe you can remember from our lectures, maybe you can remember the solution of this differential equation. The solution of this equation. How do you think? It is just necessary to open your notes about from our previous lessons and to find the appropriate formula. Okay, so I will hide this, and we have differential equations for oscillations in this simple LC circuit. And as we remember our previous lessons, we can say that the solution will be Q is equal to QF multiplied by cosine omega 0 t. Cosine omega 0 t. Cosine omega 0 t. Okay, so this is the solution, but it contains omega 0 that is necessary to define omega t plus alpha. Sorry, of course we have initial phase alpha. So we have to define QF, amplitude QF. We have to define omega 0, and we have to define alpha. Okay, so how to do this? First of all, what about omega 0? What about omega 0? Okay, maybe you can remember this value. Maybe you can remember this value from our previous exercise. No ideas. No ideas. It will be 1 divided by square root of LC. We have proved this formula on our lectures, and we used this in our previous exercise. So uh, there should not be any problems with this. Okay, and what about these values QF and alpha? How to find them? They may be found from initial conditions. And first initial condition is that magnetic field was turned off at a moment in time t is equal to 0. So magnetic field was turned off, and we may presume that at this moment, uh, there are no charge in capacitor. So capacitor is not charged in a moment in time t is equal to 0. So we can write that Q at the moment in time t equal to 0 is equal to QF multiplied by cosine alpha, and it is equal to 0 because capacitor isn't charged at this moment in time. At this moment in time. So from here we will get that cosine alpha is equal to 0. Okay, maybe you can remember how to solve this algebraic equation. Maybe you can remember how to get alpha from this equation. Cosine alpha is equal to 0. No ideas. Okay, it will be P divided by 2 plus P Pn, where n e z. So it will be n is equal to any integer. N is integer number, any integer number. So we may choose any of these values, but as we will see in future, the best choice is minus P2. So let's choose alpha is equal to minus P divided by 2. Minus P divided by 2. Divided by 2. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions. If there are no questions, so we have that it will be QF cosine omega 0 t minus P divided by 2. Divided by 2. Okay, what questions do you have? No questions. Okay, so the next step is to find electric current. How to do this? How do you think? How to find electric current? No ideas. No ideas. It will be derivative of electric charge. But we have learned this. It's derivative of electric charge. So it is necessary to calculate derivative of this value. To calculate derivative of this value. And after calculating derivative, what will we get here? According to the calculus. No ideas. No ideas. So let's remember properties of derivatives. So it will be QF multiplied by D divided by dt. And here we have cosine of omega 0 t minus P divided by 2. Okay, and how to calculate this derivative? Do you remember derivative of cosine? Again, no ideas. But it is quite simple. It will be minus QF sinus omega 0 t minus P divided by 2. minus p divided by 2. And multiplied by derivative of this expression in bracket. Okay, and from here we will get minus qf omega 0 and multiplied by sinus of this. Okay, do you have any questions? Do you have any questions about calculation of the derivative? No questions. Okay. Okay, if there are no questions, I will remove some things that we don't need more. And so we have obtained this result. But we may transform this. We may write this as qf omega 0 sinus. Let's take into account that sinus is an odd function, so we have to take into account, we may take into account this minus, and we will get p divided by 2 minus omega 0 t minus omega 0 t. And from here we may use algebraic formula or trigonometric formula and rewrite this as qf omega 0 cosine omega 0 t. Okay, do you have any questions about this? No questions. Okay, so let's remove some things unnecessary. And here, this expression we can rewrite as IF, maximum value of electric current, multiplied by cosine omega 0 multiplied by cosine omega 0 t. Cosine omega 0 t. Cosine omega 0 t. And why can we do this? Because here we have electric current, and it means that multiplier near cosine is also electric current. So from here we will get this. But where can we get IF? According to the condition, at the moment in time t is equal to 0, flux linkage was psi. Flux linkage was psi. So according to this, it means that flux in linkage at a moment in time t is equal to 0 will be IF multiplied by L. And from here we will get IF is equal to C divided by L. C divided by L. And so from here we will get that C divided by L cosine, and let's use also this formula. So we have T divided by square root of LC. Okay, this is the answer. Okay, do you have any questions? Do you have any questions? No questions. Okay, thank you. If there are no questions, it is necessary to thank you for your attention. Thank you for your attention. And we are going to finish our course. So I I may congratulate you with this. So and wish you to have a nice day.